All right, here we are. We're going to talk about the pendulum again. We're going to again change this second order ODE into a system of two first order ODEs. Go through that procedure one more time. Making there's a sort of historical note. Making precise pendulum measurements has been actually extraordinarily important in physics, and it was in fact people measuring, having theories, the calculated theory of the pendulum, and then measuring the theory of the pendulum. And so you sort of imagine yourself with this problem of developing a theory for predicting the theory of a pendulum, and then going and measuring it, and then doing stuff like measuring it in a vacuum and trying really hard to make sure you've got you understand how to measure the length, and trying really hard to get no friction on the pivot, and you have all these sort of practical problems. And then you go and you keep eliminating these practical problems, and then you notice something, particularly if you're Mr. Bessel, you notice that the pendulum period was varying if you swung it in air, and then you swung it in a different gas. And you had no theory to deal with that situation, no understanding of what that was. And you sort of made note of it, and then some other people sort of did more experiments, and then some people did extremely accurate experiments trying to figure out what was going on. And then if you were Gabriel Stokes, you took a look at all this data, and then you realized there's actually a physical situation hitherto unknown called viscosity. And then you got a development of the theory of viscosity, and then that is the boundary layer, and that is what allows you to have that ground effect when a plane is taking off. So it's actually an enormously important physical discovery that got made from doing careful pendulum measurements. That is how it came up. Okay. All right, so we're here talking about the pendulum, and what we notice is it's a second order system. This guy here tells us it's a second order system, and we want to transform this thing into a system of two first order equations. Okay, here's how we're going to always go about doing this. We're going to take the highest order derivative, in this case it's that, and we're going to put everything else on the other side. So it looks like that. Okay, that's step one. Then we're going to go down this path. We are going to associate y1. Now, in order to try to make this a little bit more clear, this y1 is a function of t. Y2 is a function of t. I don't want to have to put the declaration of what the independent variable is in there. Okay, I'm just going to call it y1. But I want you to be thinking that y1 is a function of t. So I'm going to associate y1 with theta of t. What is theta of t in this whole thing, actually? I mean, I guess what I'm trying to. What is theta? Like, is that what we're trying to find? Is what I'm trying to get at? Yes or no? I heard both answers. Okay. Okay. What does it mean to solve this guy here? It means to find theta of t. The solution is equal to find theta of t, right? We have a function, and we're saying that function is theta of t, and we're saying we know something about its second derivative, and we want to find out what the function actually is. Okay, so y1, we're going to associate with the solution, theta of t. Then we are going to take the derivative. Y1 prime is going to be theta prime of t. I'm going to associate that with y2. I just took the derivative both sides. Then I'm going to do exactly the same thing. Take the derivative. We call this y2 prime. Taking the derivative, that's going to be y1 double prime. That is going to be equal to theta double prime of t. Okay, but we know what theta double prime, this is when the procedure stops. The procedure stops here because we know what theta double prime is. That is minus GL over sine theta. And in my new scheme, theta is Y1. Now the program is basically finished. I have a vector y, which contains two functions, y1 and y2, with y1 being what I'm ultimately wanting to know. I have another vector, y prime, and that is y1 prime and y2 prime. It's a vector. And what is y1 prime in this example? In terms of y, what is y1 prime? Well, in terms of y, right? I do not want to. My differential equation has started out as a second order differential equation where my function has been labeled theta. Y2. And what is y2 prime? C over L sine y1. There. Okay, there we are. A system of two differential equations which are coupled. Y1 prime depends on y2, and y2 prime depends on y1. When we solve this, which we're going to do, we solve this using Euler's method, and our solution to the motion of the pendulum is y1. Okay, questions? This is not something you should do a few times until you can do it. I will totally confess that it's slightly confusing to do. If you can honestly keep me back and moving it like that. If you ask me 6 months to do it, I'll probably consider it out for 50 years and you can do it back. It's not, even though I've done it a lot of time, I find it a little bit difficult. So it is something you may need to do a few times. Make sure that you that you can do this. Almost inevitably, I'll ask something like this, right? This is a major move, and because any higher order differential equation, you can make this move, and then all the ODE solvers in MATLAB work on systems of first order equations. You never enter a third order equation into MATLAB. It doesn't work like that. So this is an important maneuver. Okay, let us go ahead and try to solve that. And I will do that in this way. We have an initial value problem for which we have y prime, that's right there, of t equal to f d of y. That is a statement of the system of first order differential equations. We have the specific example sitting right here. We have t varying between some limits, and we have some initial condition. In this case, our alpha, our initial condition is theta at time 0 and theta at theta prime at time 0. It's a second order differential equation, two initial conditions, function at that time, that time. Okay, so we apply Euler's method. We set the vector where we're at to start with. That's step one. We know where we are and we know what speed we're at going at. And then the update rule is this guy here. I plus 1. This is the Euler method, just written out in vector format.
We take a step size over and we calculate the new version from the old version using this right here. Out in the wrong button. Okay, let me just write that out with I'll do it this way. WI, the vector WI, in this case looks like this, WI component 1, WI component 2. That means that, for example, W naught at time t equals 0, the first component is theta naught, and W naught, the second component is theta naught. Okay, then it means that W I plus 1. So now I'm going to move to the next step. So I can go this way from 0 to 1, and then I can go from 1 to 2, etc. like that. This one, the first component is going to be WI1 plus H times WI2. Yes or no? Do you see that? Okay, that is this line right here, right? This is our Euler step. We take where we're at, and then in this case, we're adding the step size times the derivative, which is just the other component. Let's write the next one. WI plus 1, 2 is WI1, where we were before. Now, how do I get this thing right here? What is that? WI. It is. And what do I put there? How do I update? Okay. I'm doing it in two. I'm just applying Euler's method. Here, let's try it. Here, I am applying Euler's method here. That is the, imagine I had a single ODE, looks like that. I would apply Euler's method and get that, and then I go to line 2, and I apply Euler's method to this ODE right here, and I get this. So my two updates. For a third order system, yeah, I have three of them. Okay, let us just take a quick look at what that looks like. And we do that, it works actually quite well. So there's code for this on Canvas. You're welcome first, and you should maybe take a look at it. I think and there's a code there called boiler2.m in Canvas. So you can run that, and then you'll this is a graph, and on that graph is plotted two things. That is, this blue guy here is theta of t, and then this guy here is theta prime of t. So indeed, you see the periodic motion of the function. We don't have anything that looks like this. Theta t equals some function that we're plotting. We don't. We're simply taking a whole pile of points that we calculate between 0 and 5 and plotting them. Also, as a portion of having done this procedure the way we've got it set up, we also know what the velocity, the rate of change of the angle, the pendulum is, as time goes by. You can also plot it there. Okay, so there, the code is printed here. I want to make one comment about that. And that is, this code is not using vectors. It's not done using vectors. Possibly easier to sort of see what's going on. Let's just look at where the update rule is right here. That's the Euler step, right? You see this one here, that one there, and then that one. Try to make it a little bit easier to see what's going on in the code. So it's not done using vectors, but you know, if the degree for the order of the differential equation was bigger than 2, you should use vectors. Because here you'd be in a situation that, I mean, you would have, if it was a third order one, then you would have, you know, W3M and then W3 like that. It's like, right? In the sense that that's usually what you always use vectors for, right? Anyway, we would just index it. So it's not hard to code. You take a look at this, it's an extremely easy thing to code up. So you've got your initial conditions, a set of step size, you have a mesh that you want to work on, and then you simply go through and make all of those calculations. One step right there. Yep. Oh, that is the V is the order of the differential equation. Okay, so a second order differential equation results in two things here. It's not that's not the way I did that here. It's two. You have to do it twice. If it was a third order, it would be 3. If it was a fourth order, it would be 4. At some point, you would put it into a vector. You wouldn't be listed on. I think it's easier to see though the first time you see this. It's easier to see it listed out. But I want you to note that it's remarkably simple code. It's not that difficult. So this is doing the numerical calculation of the pendulum method. Okay, this is a few things to say about this method. We're going to go beyond this. It's simple. The accuracy is low. It doesn't actually, you start to accumulate lots of error, and after a while, your predictions for what the function looks like are lousy. Okay, so there are alternatives. What we want, this is our goal. Okay. Higher accuracy. Higher accuracy for roughly the same amount of work. We want to be smarter. We want to work smarter than work harder. Okay, so there's a couple ways you can go on this program. You've got a certain type of method, and now you want to do better, and you want to not increase your workload too much. You want to do something smart. There's a couple of ways you can go. You could use the sort of Taylor methods, as we've been seeing with other problems. They involve using derivatives. When we want to do a Taylor expansion, we're always finding the derivatives of the thing that we're providing the expansion. Okay, so that is a lot of things. Calculations like tedious, this is not done in practice. Calculations are tedious, not used in practice. Okay, Burden Ferris has this, and Burden Ferris, section 5.3, we're not covering it. We're gonna move to what is used, all the time. And that is what is called the, run the cutter method. And that is coming soon, that's our next section, that is, coming. And these things, do not need to. We're gonna see what you do is you take, a weighted average. A weighted average of, just more than one previous time. Calculate the next one. Anybody with that very basic description, anybody getting into their head, oh, this is very similar to something we've seen before. That's your one. It's not. Well, where do we see the idea of taking a weighted average of a bunch of stuff? Yeah. Which one in particular? It was really the Gaussian quadrature where we were. That same idea that we had with the Gaussian quadrature, we're going to use that same idea for the Runge-Kutta method, and then we're also going to have the idea of a multi-step method. And so just let's get the vocabulary here. The one-step method is the approximation for point CI plus one. So we're going to approximate something. It just depends. Involves only information from CI. I know where I am here, here, this is where I was. Okay, then we have the idea, the contrasting idea of the multi-step method. That is the approximation for CI plus one, involves CI minus one, CI minus two, etc. As many of them as you choose. So a two-step method would be like that. A three-step method would be like that. That's the idea. This is really our last topic. What we're going to do is started, so we'll take a careful look at that, and then subsequent to that, we're just going to have a very brief discussion about what to do for some types of differentiation. So the distribution is changing very rapidly. So we're going to present several values. So we're going to move to the Runge-Kutta method. Anybody got questions about this is like, actually, I'm just reading my own quote here. It's not my quote. I mean, I didn't say it, but I'm just reading the quote that I chose here. I presumably chose this a while back. There was a statement here. It's actually like, I realize it's kind of fairly hostile kind of sounding quote, but this guy This guy's really, really interesting. I think he just recently died. I think he, obviously when I do this, he wasn't dead yet. I'm pretty sure he died. But no, he's the leading expert on ants. He also has a book, a fiction, a novel he wrote called Ant Hill, which is like the protagonist is this ant expert. It's actually a pretty good book. Like it's actually really quite good. And he was at Harvard, this guy, and he has one of his thesis. Okay, so Wade Davis is Canadian, lives in British Columbia half the year, and someone here pretty sure. And he was the National Geographic explorer in residence for several period of time. First person to walk across the Bering Gap in South America, and a ethnobotanist studying the effect of plants on society. So he did actually a whole bunch of research into what's called the zombie drug in Haiti. Both this guy and that. Okay. Right, the Rangakata method. The idea is to get high order of accuracy without the need for taking derivatives of the function. So this thing here, let's just recall what that is. If we have a differential equation that looks like this, y prime equals, y squared plus 2y. There's a differential equation. This guy, f of 2y, is this part right here. Okay. We want to avoid taking that value. So, idea of the Rangakata method is to increment from our bias approximate by using appropriate weighted averages of different evaluations of this guy. And so he has been correctly pointed out, it reminds us of the same idea as in the quadrature. It doesn't have to be actually, it doesn't even have to be Gaussian quadrature. It is just a quadrature between not really right. So this one is implying that you're using zero of the Zandra polynomials, but it doesn't have to be that way. So it's the quadrature. Okay, so let's just take a look at what the two-stage. We gotta learn a bit of vocabulary here. Two-stage. First off, the opposite of this is implicit, and we are not having respect for this is not us. We're gonna stick with the explicit one. That is because the difficult and that they usually involve people root finding issue will steer the brain. So we're just gonna leave those aside for now. Okay, so this two-stage thing is going to have two function evaluations, and let me just define this one for you. I'm going to tell you that K1 is going to be H times F EI WI, and K2 is going to be H F EI plus alpha H WI plus beta K1. Okay, so what does our update will look like with this? This is a two-stage Rangakata method. Let me just write down the update for it. We'll try to parse this to make sure the time don't happen. Have over here the Euler flavor. That was like this: W equals WI plus H F plus WI WI. That's the Euler method. Now what we're going to do instead of that is we are going to start with our WI approximate, and to that we are going to add A times K1, which is H F, C, I, W, I, and then we're gonna add B times H, F. Plus alpha H, W, plus beta. K1 is H, F, C, I, W. Okay, I just, you do not need to write it out like this. I think you can see, now that I have written it out like this, that it is, I think, a little bit nicer to write out this way. What you're doing is making two function evaluations. You make this function evaluation, and you make this function evaluation. Two function evaluations. And then you update at the next step over based on those two functions. Averages, if you're going to weight them. So there's some things we don't know in this, what I've written down. There are, unknown. Okay, we're stuck with, we've chosen already H, and I mean, TI is our independent variable at the I1. So the things that we can actually choose here, the unknowns, we can choose how much to move over. We can choose how much to add that variety, that previous calculation. We can choose that, and then we can choose this, and we can choose this. We're going to use some kind of a rule. So I'm saying here is the two-stage the Rangit-Tata rule for which you can adjust alpha, beta, A, and B. So what we want to do now, just like we did with the Gaussian budget routine, we want to choose these guys, alpha, beta, A, and B, to maximize order of the method. So we want to do like a part of okay. Questions about this step that we made coming from the basic Euler method? Okay. So our goal is to maximize the order of the method. Okay, we're going to recall what that means. The method order as local truncation error. The local truncation error is this. The actual function at I plus 1 minus the actual function at I plus H times y C I y I. So it is the difference between what the function actually is at the I plus first thing minus the approximation rule applied to the actual value at the I step. That is the local truncation error. And that is order, that is OH of P plus 1. And that P, whatever that P is, that is the order of the method. Okay. We already said this, the number of stages of an order is the number of evaluations of a function. Function evaluations are extensive. And I know we mentioned we're discussing extensive. I will point you to at least what, how you would recognize an implicit method, but we do not have time. We will not go there. Okay. So let's now taking a look at determining how can we pick. Now the thing is, we've got this idea of solving our differential equations with an update rule like this. Now we're gonna try to say, what is the state choice and the best choice for alpha, beta, A, and B? That's the idea here. Not gonna be able to finish this, so I think what I'm gonna do is I'm gonna lay out something, then we're gonna take pause to think about it, and then we'll come back on Friday. I don't wanna rush this. Okay. So our update rule, one fell swoop, I wrote this down earlier. Our update rule looks like this. We have an ith approximate, and then we want to go H times A and BIWI, plus B times BI plus alpha H, WI plus beta H. So what we're thinking here is it looks a little bit cumbersome and possibly scary, I don't know. But all we're really doing is saying we have some previous time, some previous approximate. That is this thing here. We know this. Like that. We are going to H is we're gonna pick the step size 8. So we're gonna have that as a given. That is known here, here, and here. Now what we're going to do is we are going to try to figure out for an optimal value of this, and this, so that we maximize the accuracy. First thing I'm going to do is introduce a variable for this. I'm going to call this something. So a big thing here. This is 5. So really what we're doing is we're taking WI plus, you're calculating it as WI plus A times the big in. Let's see if we can write the local function error. You just come here. Local function error. That is going to be yi plus 1 minus. What do I put that? What do I put right there? If I want to write the local truncation error, yi plus h times this. Okay, so what we're doing, this is correct. Thank you. What we're doing is we're saying here is the exact value at I plus 1. Here is the update rule applied to the exact value of the I'm going to write down one more statement. Taylor's theorem here. Okay, the exact solution at time I plus one is the solution at time I plus the step size times the derivative at time I plus step size squared over 2 times the second derivative. I know it, I'm saying second derivative, I'm writing first derivative, but think about this. This is y prime. That's our differential equation, right? Y prime is equal to f at ty. This is Taylor series. And then there'll be some more things. Let's look at f prime at ty. F prime at ty means what? Derivative with respect to t of f of t and y. And let's make it obvious or note to ourselves that y is itself a function of time. That means this will look like this. Y dt, y dt of f of t y plus this on which brings instead. Then we'll take the derivative with respect to y and multiply by y. This is implicit differentiation. Let me just, I'm just gonna put an example here. Okay, here's my example. Imagine, it's just an example, imagine the situation, f of t y, looks like this. T squared, y squared, plus sine y. Okay, that would mean that this differential equation is this, y prime is t squared, y squared plus sine y. That would be the differential equation. And so this is our function right here, f of ty. It's a function of t here. Now I want to take the derivative with respect to t of this thing. This is a function of t. So my derivative here is going to be 2t times y squared plus t squared times 2y, y by dt, plus cosine y, y by dt. That is what the statement is right here. This is that. Right here, and we have a function that is function of. And that is where I'm going to stop. Because now I'm going to go through and use this. I'm going to need to take this derivative here. And I'm going to need to go first. The good thing to do is to look this through and make sure you understand these steps so that when we start next time, we're all kind of like, okay, we see what's happening. We will have an influence on the beginning of the class on Friday. Then we'll I do.